Hello. We've already used the truth tree technique in sentence logic. In sentence logic trees, we broke down sentences into smaller sentences in such a way that the shorter sentences further down in the tree made the longer sentences above true. For instance, A and B would be broken down into a stack of two sentences, A and B, which together are enough to make the larger sentence A and B true. So we check A and B because we're done with it. We can't do anything else with it. B or D would be broken down into two branches, C or D, since either of these two sentences is enough to make C or D true. Likewise, if we take the set comprised of A and B and C or D, we end up with two open branches, and each of these two branches contains a set of atomic sentences that is enough to make the initial set true. In the end, the process of breaking down SL sentences into smaller sentences is guaranteed to end. The ending points are marked either by contradictions or by sentences that can't be broken down any further. Thus, we end up with a set of branches, open or closed. The branches that remain open will contain a set of literals, which, as you'll remember, are themselves atomic or negations of atomic sentences. Each of those open branches will correspond to a way of making the sentences in the initial set true. That is, each of them corresponds to a set of assignments or to a set of rows in a truth table. We use truth trees as a mechanical method to test primarily for consistency of sets of sentences, but also in order to determine other properties such as validity and invalidity and all the rest. Last, we can also use truth trees to read assignments of truth values off of the branches of the tree. So, from the branches of an open tree, as you remember, you can extract a model for a set of sentences, or a counterexample to an invalid argument. We can also use the method of truth trees in predicate logic to test for consistency, validity, etc. The mechanics of the procedure are mostly the same. However, you no longer think about the tree as the process of coming up with truth table rows or assignments. Rather, working on a tree branch in PL is a way of arriving at an interpretation. Remember, an interpretation is a domain and a set of truth assignments. So, working on a tree branch in PL is a way of arriving at an interpretation that makes every sentence in a given branch true. When doing truth trees for predicate logic, we're going to incorporate all the rules that we use for SL trees. So I hope you remember those. If your memory needs refreshing, you can watch your videos for SL trees again. Remember that we had two rules for each connective. One for those in which the connective in question is the main operator, and another one for those cases in which the connective is in the scope of the negation. Again, here I'm just refreshing your memory. However, we'll introduce four new rules to deal with predicate logic. And we have one for each of the quantifiers and one for each of the negations of the quantifiers. Let's begin with the universal rule. Let me give an English example to give you an intuitive idea of how it works. 1, everybody loves Al, and 2, Beth doesn't love Al. Suppose that our domain is a people in an office in which Beth and Al are co-workers. So you can interpret 1 as everybody in this office loves Al. Now, can we devise a mechanical method that will tell us whether these sentences are inconsistent? After all, 2 is not the direct negation of 1. Well, to do this, we can rely on the fact that 1 has consequences that directly conflict with 2. Consider 1, everybody loves Al. But if 1 is true, every member of the domain loves Al. And since Beth is a member of the domain, then, if 1 is true, then Beth loves Al. So we get 3, Beth loves Al. But then we have a direct contradiction between 2 and 3, which tells us that the initial pair of 1 and 2 wasn't consistent, since 3 is a pretty transparent consequence of 1. Now let's put this example in the form of a PL truth tree. To vary things a little bit, I'm going to go into Blackboard mode. Okay, so here we are in the Blackboard. Well, let's put this, as I said, we're going to put this example in the form of a PL truth tree. So let's represent everybody loves Al in this way. and Beth doesn't love Al in this way. Okay? Now, when we did truth trees for sentential logic, we were very informal in terms of the format. But since now we have more things to keep track of, we're going to be more strict in our bookkeeping. And we're going to add number lines and step justifications, just as we did when we were doing derivations. So I'll start by assigning a line number to each of the sentences in the initial set. Okay? Now let's do what the universal rule tells us to do. So first, we have to gather all the names that are being used at this point, and there are only two names, A and B. Next, it tells us to write at the bottom, for each of the names in our list, a substitution instance. And remember that substitution instances of universal sentences are obtained first by deleting the quantifier to the left, in this case every x, and then uniformly replacing all the occurrences of the bound variable x in this case with a single name. So we have two names, A and B. So we have the A for x substitution instance, which in this case is LAA, and the B for x substitution instance, which in this case is LBA. And so both are obtained from line 1 by the universal rule, which we haven't defined so far, but which we'll define in a second. Okay. Now compare lines 2 and 4. There is a direct contradiction between not LBA and LBA. And that means that the tree is going to close, right? And the sentences there's no single interpretation that will make both sentences true. Also, before I forget, something that you do also, and we'll see why, is that to the left of the quantifier, we write the letters that we use to derive substitution instances. Okay, back here with some important points about the proof we just did. First, you have to write a substitution instance for each name in use in the branch. Actually, we didn't need to write LAA in our previous tree, since it's not doing any work. But it's a good idea, at least when you're starting out, to write a substitution instance for each of the names that are being used in the branch you're working on. So, for instance, at this point in this tree, you have three names in use, A, B, and C. So when it comes to exploiting the quantified sentence in line 1, you will need to write three substitution instances, namely FA, FB, and FC. Another point is that you can, and indeed you must, re-exploit the universal sentence rule for each name in use at the branch you're working on. Now, there are rules, as we'll see, that require us to introduce new names. So it could happen that later in the same branch of the tree, we have a sentence that introduces the names D and E. Then we'll have to derive the respective substitution instances for our initial universal, which would be FD and FE. And then we write to the left of the universal sentence the two new names that have been substituted for it. Third, and relatedly, when you have used the quantifier rule, you don't check the universal sentence you applied it on. This is because checking a sentence means that the potential of the sentence has been exhausted. You cannot exploit it anymore. This is true of the truth functional sentences of SL, but not of universals. A universal is still alive even after you've substituted all the names present in the domain. And this is because, as we've said before, there are rules that introduce new names in the domain. And every time you introduce a new name, you have to reuse the universal rule on the universal sentence. So, while the tree is in progress, the universal is usable and unexhausted. Fourth, you might encounter a case in which there are no names being used at all. Here, since we stipulate that every domain has at least one individual, we can introduce a new name, so as to be able to apply the rule. So, without further ado, we can define the universal rule for PL trees. Remember that U stands for any variable. Okay, here we go. If a universally quantified sentence appears at some point in a tree, do the following to each branch at which it occurs. First of all, collect all the names that occur in the branch. And if no name occurs there, introduce one. Second, write at the bottom of the branch one substitution instance for each of the names in use. Third, write a list of the names you just used to the left of the universal sentence you just exploited, while also refraining from checking it. And here's basically what I just said, but in a more graphical and condensed form. Before we proceed any further, let me warn you. This rule can only be applied to sentences whose main operator is a universal quantifier. So it wouldn't be applicable here, since the main operator is not either of the inverted A's, but the V. Likewise, you can't apply it to sentence 4, because the universal quantifier is within the scope of a negation. So let's go back to the blackboard to do a couple of exercises. Okay, let's do this other example, and here we have a set of sentences, and we're asked, well, is this a consistent set? So we're going to use our truth tree method. So first, we assign numbers to the lines, 1, 2, 3. Okay, the only sentence that I can exploit here is the universal, since the other two sentences are literals. So what I'm going to do is that on line 4, I'm going to write the substitution instance of the sentence in 1 with A, because I'm going to use the sentence, the name that is already in circulation, which is A. So it's going to be FA or GA, and that is by the universal, which is in 1. And I can add 1 here to the list of names that are being used to exploit this sentence. Okay, now notice that I have a disjunction, and I can apply the disjunction rule to this. And I can do then, in this line, FA or GA, here we have a branching situation, and this is by the disjunction rule, the V rule at 4, and I can check it. Okay? Okay, so here I'm at the point where I can't develop this tree any further. And so I have 2 branches, okay? And so what about the left branch? Well, notice that the left branch contains not FA, and it also contains FA. So it is, it contains a contradiction. It is a closed branch. And what else do we have? Well, we have here on the other branch, we have not GA, and we have GA. And so it's also a contradiction. That means that there is no model for this set. That means that this set is inconsistent. Okay, now let's do this other example, which has a slight difference in that now we have another name. Instead of not GA, we have not GB. So let's begin by adding some number lines. Here we have 1, 2, and 3. Okay, and so the first step is to exploit the existential. So we have 2 names. That means that we're going to do it with each of the names. So let's start with A. So on line 4, the substitution instance with A would be FA or GA. And this is by the universal rule in 1. And then I'm going to write A to indicate that I've already used that name here. So at this point, I could use 2 things. So I could get the substitution instance of the universal, but now with B, or I could break up the disjunction. Well, you could go either way, but I'm just going to break up the disjunction first. So I'm going to write FA, and I'm going to write GA by the V, and here line 4, and I can check it. Okay? Okay, so on line 6, well, notice that if you compare line 2 and line 5, I have not FA and I have FA. So I have a contradiction. So it would be perfectly okay to add an X here at this branch, right? And declare it closed and just continue with the rightmost one. But for the sake of completeness and to give you a complete illustration, I'm just gonna proceed to develop both branches. Okay, I'm gonna add the fiction that this branch is open. So now I'm gonna get the substitution instance of 1, but with B. Okay, so and I have to do it for all the branches that are available. So I'm gonna do here on the left one, I'm gonna do FB or GB. And then here I'm also going to do FB or GB. And this is, again, by the universal on 1. And I write here that I just use the B. Okay, now the last step is to break up these individual disjunctions here. So here we would have FB, and here we would have GB, and the same here, FB and GB. And I'm gonna check them and say that this is by the V on 6. Okay, now I'm finished with this tree. I have no way to develop it further, so I have to check whether I have any contradictions or whether I have any open branches. Okay, well, we already know here that between FA and not FA, I have a contradiction. And so this is the branch that begins with not FA here and ends up with FB at the bottom. So this one is closed. And that also affects this second branch from left to right, right? Because this branch, these two nodes are common. So we do this. Now, what happens then in the third branch from left to right? Well, I have not FA. Do I have FA? No. I have this disjunction, but I don't have FA on its own. I have not GB. Do I have GB on its own? No. Right? I have this disjunction, but again, I don't have GB on its own. I have GA, so I don't have not GA. So this seems to be perfect. What about the rightmost branch? You know, there seems to be some trouble since we have not GB and I have GB. So this one, again, closes. So we have one open branch. And this means that this set of sentences is consistent. And what is more, we can develop an interpretation, right? We can extract an interpretation that we make all of the sentences in this set true. That is, it will be a model. And so this would contain a domain with the names A and B. And then what are the truth values? Well, we have FA, GA, and we have FB and GB. Okay? And we're going to read the truth values of this open path or branch. Right? So we have not FA, not GB, GA, and FB. So not FA tells us that FA is going to be false. Not GB tells us that GB is going to be false. GA tells us that it's going to be true. And FB tells us that this is going to be true. So that means that when we adopt this interpretation, we're going to make sentences 1 to 3 true. And you can verify this on your own. Okay? Now let's take a look at the rule for the existential. How do we exploit an existential sentence in a truth tree? This time I'm going to flip the order of presentation. I'm going to introduce the rule first, and then I'll make some comments on it. The rule goes like this. If an existentially quantified sentence appears at some point in a tree, do the following to each open branch in which it occurs. First, pick a new name, that is, a name that hasn't previously appeared in the branch in question. Then, at the bottom of the tree, write the substitution instance of the existential sentence using the new name you introduced. Third, put a check mark on the existential sentence you just exploited. In parentheses, here I'm going to issue the same warning that I mentioned earlier. This rule is only applicable to those sentences whose main operator is an existential quantifier. Here's a very simple example. Suppose that at some point in a tree, I have these two sentences. I need to exploit the existential sentence, so I have to choose a name. The name A is already in use, so I have to pick another name. So I choose the name B, and on the following line, I write the substitution instance of the existential, which is FB. Then I write the justification. And finally, I check the existential sentence to indicate that I'm done with it. At this point, you may be asking yourself, why do I have to pick a new name? And why do I have to check existential sentences when I was just told not to check universal ones? Don't worry, I'll address each of these questions in turn. New name. So why a new name? Well, if you remember, back when we were discussing the natural deduction rule of existential exploitation, we insisted on the requirement that every time we exploit an existential quantifier, the name we use must be isolated. Also, we ensured isolation in part by choosing a new name every time we exploited an existentially quantified sentence. You should re-watch our video on existential elimination in case you want to revisit the reasons why we adopt this policy. But basically, this was an effort to prevent our derivation rules from misfiring. In the same way, and for similar reasons, the new name requirement here is also a safeguard. For instance, suppose that we have this sentence pair. 4, Al is not a thief. 5, someone is a thief. This is obviously a consistent pair, since the person that makes sentence 5 true could be someone other than Al. This would be made true, for example, by a domain consisting of Al and Beth, provided Beth is a thief but Al isn't. But suppose that instead of thinking about it, we proceed mechanically and produce the following tree to determine the consistency of this pair, which is the predicate logic translation of sentences 4 and 5. The next step is to exploit the existential sentence. So suppose that I simply choose the name that is already in use, namely A. Then I get TA on 3. But now I have a direct contradiction between lines 1 and 3, and so I close the branch and conclude that the pair of sentences at the top is inconsistent. But this would be an obvious mistake, since we know that the sentences in the set are perfectly compatible. This could have been avoided if I had chosen a new name to exploit the sentence in 2. The only name being used in this branch is A, so I can choose any other name. I could have picked B, C, etc. In this case, I'm going to pick C. So what I'm saying is that someone in the domain, I don't know who, is a thief, and I'm going to give that person the temporary name C. And then I check the existential sentence. I'm done with the tree, and it remains open, which means that the set of sentences is consistent, and this is the correct result. This open branch provides us with an interpretation that functions as a model for the initial set of sentences, namely a domain comprised of A and C, in which TA is false and TC is true. Also, notice that, unlike the case of the universal, here you can check the existential sentence once you've exploited it. This is because the truth of the substitution instance you derive below guarantees the truth of the existential sentence above, regardless of how many new names you introduce in the domain. For example, an inner example, TC makes there is an XTX automatically true, and there is an XTX will continue to be true regardless of what happens to other individuals in the domain. So we're done with the existential. It is now dead in this branch. Notice that, unlike the universal rule, the existential rule does not require us to make the sentence true of all the individuals in the domain, but only of one. One is enough. Also, not only is it the case that you can check the sentence, but also that you should do it, since reusing the sentence by reapplying the existential rule could lead to confusion. So, to conclude, once you exploit an existential sentence, you check it, because you've already expressed all that this sentence means. The only sentences you reuse, remember, are universals. To make the contrast between the two rules clearer, consider again this example, which we saw earlier. When we exploit a universal sentence, we have to write substitution instances for all the names that are in use, and we leave the universal sentence itself unchecked. But when we're dealing with an existential, we only write one substitution instance, using a new name, which here it's D. Then we check the exploited existential sentence. Okay, let's do a couple of examples that combine the two rules. Now we have another example in which we have a universal and an existential quantifier. So we may start by assigning the numbers here. So we have a universal and an existential. Both are exploitable, so where should we start? Well, a good advice, and a very good advice, that is that whenever you have a universal and an existential, exploit the existential first. So repeat this. Exploit the existential first. So this would prevent you from having trees that are going to be unwieldy and which are messy and which will probably lead you to error. So remember, keep this in mind. So there's the proviso that we have to use new names. There are no names already in use, so we're simply going to use the first name that comes to mind. We can use any name. Let's use A. So on line 3, we can write not BA and AAA, and this is by the existential on 2. And we can check it. Now, well, we can simply break up this conjunction, and then on line 4 we do not BA, and then 5 AA. Remember that this rule gives us a stack, and this both come from the ampersand that we have at 3. Okay, now we are ready to exploit the universal. So on line 6, we use it with the name that is already in use, which is A. So we write if AA, then BA. And this is by the universal rule in 1. And we write the name that we have already used. Okay, so we are left with this conditional that we can break up by means of the SL rule of the conditional. So we simply write not AA and then BA. And this is by the conditional in 6. And why do I get? Well, in the leftmost branch, you have AA, and then you have not AA. And then on the rightmost branch, you have not BA, and you have BA. So that means that all the paths close. That means that this set of sentences is inconsistent. Okay, now let's do this example, and this is given to us in English. And it says, every anarchist is a millionaire, so millionaires play golf. Al is a millionaire who doesn't play golf. So we can start by translating the sentences and say, every anarchist is a millionaire. If something is an anarchist, then it is a millionaire. Now we have some millionaires play golf. Let's use G as play golf. And then we have a non-quantified sentence. Al is a millionaire who doesn't play golf, which, if you remember, can simply be translated as Al is a millionaire and Al doesn't play golf. So we can give it the name A. All right, so we have these 3 sentences. Again, we have a universal, we have an existential, and we have non-quantified sentences. Since it looks like the most straightforward thing would be simply to check the conjunction, and then I'm going to write the stack conformed by AA, and then not GA, and this come from the ampersand at line 3. Okay, now I'm only left with the universal and the existential. And remember, we use the rule of thumb that whenever you have a universal and an existential, you exploit the existential first. So the rule that introduces the names, you exploit first. So I'm going to use, and remember that I have to use a new name. We already have the name A in use, so I'm going to use, let's say, B. So here on the next line, I have MB and GB. And this is by the existential in 2. I already exploited this, so I can check it. I don't have to worry about it anymore. So we have a conjunction. So let's break it up. 7 and 8. We do this by the ampersand in 6. Okay, now it's the turn of the universal. So we're going to, on the next line, write A. We have to remember that we have to use it with all the names that are here in the branch, and we have 2 names, A and B. So let's start with A. So we have A here. I'll make it smaller so you can see the whole. AA and MA. And so here this is by the universal in 1. And I write the name here, A. Okay, and this is a universal, sorry, this is a conditional. So I can simply go and write on line 10, not A, MA. And this is by the horseshoe on 9. I think you can see it here. This is by the horseshoe 9. And okay, now on line 11, well, what do I get? Notice that I have here on line 4, I have AA, and on line 10, I have not AA. So it looks like that branch is closed. So I'm here, sorry, let me see if you can see it, right? So I still have to write the substitution instance of the universal with B, but I only have it to do it on one branch because I have only one open branch. And so I do it here on 12, AB, then MB, and that is by the universal on 1. And I write this other letter, B, right? Okay, and I have this is a conditional, and so it analyzes into not AB and then MB. Okay, as you see, let me see if you can see the finished tree. As you can see, then I have these two lines. Well, is there any conflict here? Well, it looks like we can see no contradiction here. So it looks like these two branches remain open. So the set of sentences is indeed consistent, and you can develop some models from it for this set of sentences. I'll let you do it at home. 2 more rules. As you know, sometimes we'll encounter sentences in which a quantifier occurs immediately after a negation, such as 6 and 7. The 2 rules that we have so far won't allow us to break down these sentences, since they only apply when the sentence is the main operator. However, we can take a page from our natural deduction book and add a couple of quantifier negation rules. From previous lessons, we know that the negation of a universal is equivalent to an existential with a negated scope. In consequence, not for every x fx is equivalent to there is an x not fx, which is a sentence that we can exploit with our existential rule. Likewise, the negation of an existential is equivalent to a universal with a negated scope, which is a kind of sentence we can manage with our universal rule. Hence, the sentence to the left can always be replaced with the sentence to the right. So we can formulate our 2 new rules dealing with quantifier negation. Let's start with a rule for the negated universal. If a negated universal occurs as a full sentence, write the equivalent existential quantification of a negated formula at the bottom of every branch in which the first sentence appears, and then check it. And here's the same, but in diagram form. Now, notice that we are allowed to check this formula. This is because we replace it with an equivalent one, and so we don't need it anymore. In fact, if you cross it out, I wouldn't be mad. Then there is a corresponding rule for negated existentials, which predictably enough goes like this. If a negated existential occurs as a full sentence, write the equivalent universal quantification of a negation at the bottom of every branch in which the first sentence appears, and then check it. Again, here's the diagram. So to deal with quantified sentences in truth trees, we'll be adding 4 rules in total: universal, existential, universal negation, and existential negation. Okay, this is all for now. This video dealt with the fundamentals of the truth tree technique as applied to quantify sentences in predicate logic. In subsequent lessons, we'll deal with multiply quantified sentences and with the use of truth trees for determining the validity of arguments. Bye.